2.3, the precise definition of a limit. That's all you have to write from this slide. We need to find a more precise definition for a limit. We can't have terms like arbitrarily close to, which is what we've been using so far, which is where we kind of pick a number that's close to the number we're trying to find the limit of. But we haven't said how close it has to be. We need to find a way to come up with specific conditions that can be applied to any example. So with our new definition, we're going to prove that the limit properties given in the previous section are true. We can establish other particular limits important to the study of calculus. You should write this. To show that the limit of f of x as x approaches x naught, so that just means as our x is getting closer to some number we chose, that's what x naught means, equals the number L, we need to show that the gap between f of x and L can be made as small as we choose. So in other words, if x is close enough to x naught. So we start by setting the gap the size of the gap between f of x and L. Example 1, we're going to look at a linear function. So consider the function y equals 2x minus 1 near x naught equals 4. We can tell that y is close to 7 when x is close to 4. So our limit as x approaches 4 of 2x minus 1 equals 7. But what we're looking for is how close to x naught equals 4 does x have to be so that y equals 2x minus 1 differs from 7 by 2 units in this case. So what I'm really saying is I want my y to be within 2 units of 7. So that means I'm looking for what values is the absolute value of y minus 7 less than 2. So we need to solve that. In order to figure out what values that would be less than 2, I have to go back to my old methods, which is why we reviewed all that Algebra 2 and pre-calc stuff in the beginning. If I have an absolute value inequality, that means I need to do y minus 7 is less than 2 and greater than negative 2. Now in order to solve for y, I add 7 to both sides. This gives me y is less than 9 and greater than 5. So if I want my y to differ from 7 by 2 units, or within 2 units, then that needs to be between 5 and 9. So we found the first part, which is to say that in order for my y to be within 2 units of 7, my upper bound has to be 9 and my lower bound has to be 5. Right? Because it's got to be between 9 and 5 to be within 2 of 7. Which then means that I need to restrict my x. So I have to find what I would plug in to get 5 and 7. So I can solve the equation. This one's simple because it's a linear equation. It's a very simple equation. I would just do 5 equals 2x minus 1. Add 1 to both sides. It gives you 6 equals 2x. Divide by 2, x equals 3. That's my lower bound for the x's. To find my upper bound, had a good question. The question was, where did the 5 come from? Our 5 is the y value here. So when I plug the 5 in for y, I'm looking for my lower bound. What x would give me 5? So when I plugged that in, I solved and found x equals 3 would give me 5, or y. Now we do the same for 9. So I'm going to plug the 9 in for y, and that gives me 9 equals 2x minus 1, and now I just solve that. 10 equals 2x, divide by 2, x equals 5. And when x equals 5, y is 9. So what we found is if I wanted to restrict the y to being, it has to be within 2 units of 7, then my x has to only be restricted by 1. My x has to be within 1 unit of 4 in order to give me a y that's within 2 units of 7. Because 3 is only 1 less than 4, and 5 is only 1 more than 4. So that's our basis here. We're going to restrict our y's first, and then we're going to find out how close our x's have to be. So x has to be within 1 unit to solve this. Now, I want you to keep this example problem in mind as we proceed through the definition, because when you look at the definition, you're going to be intimidated right away by the fact that there's epsilons and deltas in it. But don't let it intimidate you. We're restricting the y first, and then we're going to use that to restrict the x. In this case, we had placed a restriction on y of 2. It's not always going to be that simple, as you're about to find out. So, we're actually going to define the limit of a function. Let f of x be defined on an open interval about x naught, except possibly at x naught itself, which means that all around the number that we're getting close to, it has to be defined, but not necessarily at that number. We say that the limit of f of x as x approaches x naught is the number L, and we write it, the limit as x approaches x naught of f of x equals L. If for every number epsilon greater than 0, there exists a corresponding delta greater than 0, and I'll let you have some time to write that down. So if we have an epsilon greater than 0, there exists a corresponding delta greater than 0, such that for all x, the absolute value of x minus x naught is between 0 and delta. Then the absolute value of f of x minus L is less than epsilon. In other words, if I take my value of the function minus the limit, that has to be less than some number, like in the last example we did, it had to be within 2, then we were able to come up with a x that made that work. So if I restrict the x's, there's a restriction that I can place on the y's. If I restrict the y's, there's a restriction I can place on the x's. And I'm able to find out what each of those is. Here's a way to look at it graphically. If I take that epsilon that I just put in, then here's my limit. My f of x has to fall within these two, where I'm adding my range that it has to fall within, and I'm subtracting my range that it has to fall within. And if it has to fall within here, I can do the same thing with my x naughts and my deltas. So that if it falls within here, then it's only going to work for all x that are between these limits here. So this is going to be true for all the x's within this interval. So just to kind of wrap up today, I'm going to show you how this applies to the first example. We started with f of x equals 2x minus 1, right? And I wanted to find the limit of f of x as x approaches 4. So I started and I found my limit to be, just by plugging in, since there was nothing that would ruin it, 2 times 4 is 8 minus 1, gave me a limit of 7. Then I said I wanted to think about every value that was within 2 of my limit, which meant that I had to restrict my epsilon and say that was epsilon equals 2. In other words, I could go 2 above my limit, or 2 below my limit. Then that said, what are my x values that will make that true? So my x naught is what my limit was as x is approaching, which was 4, and then I found my x values that made it true, which were 3 and 5. So what do I have to add to 4 to get 5, and what do I subtract from 4 to get 3? 1. So that was delta equals 1. So I had an epsilon that I decided to set, and it had to be within 2, and I said that means my x's have to be within 1 of 4 in order to make this true. We will have plenty of examples to go over with this. But just kind of wrap your head around what we're trying to figure out here. We're saying that if we're trying to get within 2 of this, then we had to be within 1 in our x's.